All right, let's go ahead and get started. You've turned in homework number 2. Homework 3 is going to be available after class on MU Online, so you can get a start on that. It's essentially going to be very closely related to the in-class exercise that we're going to be working through today during class. In our next meeting, you're going to have the opportunity to use your computer to solve some of the problems, and so you're welcome to use these computers that are in the room. If you'd rather utilize your laptop, then bring it. It's Microsoft Excel that you're going to need to have access to for our next class meeting. All right, so today we're going to work on a more complicated column of that factor table. We've already talked about future values, present values, annual uniform series, but today we're going to start talking about gradients. Before we get into it, are there any questions about these announcements? Yeah.
Will there be any future lectures that require us to have our own personal laptop, or?
No.
Okay.
No. All right, so just to review, here's an annual series. And remember that the standard form of an annual series is that the amount each year is the same. That's what makes it a uniform annual series. And when we call it an annual series, that's a little bit of a misnomer because it could be a monthly series or a quarterly series. It's just that there is, during each period, the same amount. And so with the factor table, we can solve for a find P given A type problem as long as the amounts are equal and consecutive. If there's a gap, for instance, if there was no payment in year 3, then that annual series would be broken, and we'd have to treat it as 2 separate problems rather than one continuous annual series. One other thing I'll point out is that the general standard form of these is that you're solving for a present amount that's 1 year before the first of the consistent uniform payments. And so you'll notice here that P is in year 0, and what we're calling year 1 is the first time that we see one of those uniform amounts. So that is how we would find P given A. You can do about the same thing. It's just a different table factor if you want to work with a given P and find an unknown A. And so an example of a real-world application of this is if you are making a loan or taking a loan, and then you want to find out what the uniform repayment amount would be. So that would be an example of a find A given P. And again, there's that 1 period gap between the present and between the first time you see the uniform amounts. Okay, so the factor tables are both at the back of your book, and also I've mentioned the FE exam that a lot of students will take during their senior year or shortly after graduating. And so this factor table is taken from the reference manual they provide for the FE exam. And so you'll notice that this would be find P given A, and there are these G columns that we're going to be talking about today, the gradients, which are a little bit more complicated, but in some ways they share some of the same characteristics of an annual series. So just as a quick illustration of an annual series, comparing the text of a word problem to how we would represent it as a cash flow diagram and solve it, we believe that buying a certain thing is going to add $5,000 a year in extra revenue, where we have an interest rate environment of 10%. And so how much could the company afford to spend? So we're trying to find out if we are going to receive this extra revenue for 5 years, then what's the present equivalent of it, the economic equivalent of $5,000 a year for 5 years when I equals 10%. And so this is what it would look like as a cash flow diagram, where these amounts we're going to be receiving, and so they're arrows up, and we're trying to figure out how much should we spend now to be in balance with this opportunity. So this is find P given A with I equals 10%, N equals 5. And so we would go to the factor table and find P slash A 10%, N equals 5. Look up the factor for that, multiply it by the amount of the A, and then that gives us the present value we should spend now. So 18,954. All right. So if we want to move an annual uniform series all the way to the future, then the standard notation for that is that the future amount is in the same year as the last repayment. And so you'll notice here that there is an amount you're receiving in year 5, and that's also when you would pay back the amount of the loan. And so that's just the standard form of an F/A. So find F given A. Again, the amounts have to be consecutive with no gaps, and they all have to be equal in magnitude in order to do an F/A on a cash flow diagram like this. We can also find the A from a known F. Now, future amounts, like an unknown future amount or a given future amount, the common real-world application of those is if you're going to be selling a piece of equipment or selling a business. So for instance, if you know that you have been receiving revenue over a certain number of years, and now you have to pay back someone at the end of that period, then that would be an example of where you're finding F given A. All right, so here's the 8% table, the column for find F given A or find A given F. So we just go for whatever interest rate we've got to the page that applies, and then the row would correspond to the number of periods that annual amount is recurring. So here, a certain modification is going to save $10,000 per year. That's money that used to be spent, and so we consider that as a revenue. Even though it's not a direct revenue, anytime you save money that previously has been a cost, you consider that as a revenue. So for 8% per year, how much will the savings amount to in 7 years? And so it would be easy if you didn't know how to solve these types of problems just to say, well, it's 10,000 times 7. But the problem with saying 10,000 times 7 is it wouldn't take into account the time value of money. It wouldn't take into account the idea that the money in year 1 has a different value than the money in year 7, because costs are always changing. And so what this is really saying is find the equivalent in year 7 of this annual series. And so if we're going to express it as a cash flow diagram, this is saying you can save $10,000 each year for 7 years, or what's the future lump sum equivalent of that same series? If we wanted to just have it be one big amount at year 7 instead of the annual amounts every year, what would it be? Okay, so this is find F given A, I equals 8, N equals 7. So F/A, 8% interest, N equals 7. We'd go to the factor table, multiply it by the magnitude of the A, and that's where we get the future value would be 89,228. All right, so that's just an illustration of the standard form that a uniform series will take on. What is somewhat similar in some ways are gradients. Now look at what's happening here in this cash flow diagram. We're trying to find some present value for a series of expenses. So the arrow down means that we're going to have to pay. In year 0 we're paying nothing. In year 1 we're paying nothing. In year 2 we have to pay a certain amount. So maybe G is 100 or 1,000 or whatever. It's just some amount. But in year 3 we have to pay twice as much as we did during the second year. In year 4 it's 3 times whatever this fixed amount is. And so it keeps increasing by a constant amount each year. So the first thing I'll point out for you is that we're calling 0 now the present, where we would try and find out how much should we receive today in order to be willing to pay all of these amounts over the course of the future. This is a very strange loan. I'm not sure what kind of a bank would say that you have to pay nothing next year, but then in 2 years you have to pay 100, in 3 years you have to pay 200, in 4 years you have to pay 300. There probably isn't any bank that's giving those kinds of loans, but a gradient is a useful thing because sometimes we do see costs going up each year. So the cost of maintaining equipment, the expense associated with fuel, because fuel costs are going up, and so knowing how to solve gradients is just useful as a tool, even though it's pretty uncommon that like a financial arrangement would be structured exactly as a gradient. So there is an equation for each of the same things that you can find in the factor table. So for instance, if you want to find the present value of a gradient, here's the ratio. This entire equation is the ratio of P divided by G. Or if you're trying to find the future equivalent of some gradient, then we have the equation for that as well. All right. So let's get a practice on solving gradients with the in-class exercise that I got for you today. Let me hand that out. Okay, the first problem on here is kind of just a, I don't know, get the mental juices flowing review type question. But on the back side of the paper are a couple of problems, problem 2 and problem 3, that I'm trying to step you through the idea of thinking about gradients with like step A, step B, step C. It's kind of to guide you through solving your first gradient. Okay, problem 1, the first one. So you are giving a loan, so that's going to be an outflow of $7,500 at the present. Now it doesn't say specifically at year 0, but that's the default assumption. Is if it didn't tell you which year it happened in, you can infer from that it means it's happening now. So you give a loan of $7,500. I equals 0.8, n equals 8. So you can see I've summarized that here in the parentheses. And this is kind of our shorthand for explaining what type of a problem it is. It's an A/P problem where you're finding the repayment amount, and it says it's going to be equal annual amounts over 8 years. So that's where we get the clue that this is a uniform series. And we can go up to the table. This is the 8% table, and this is an A/P problem. So we go to the column that says A/P, and those are called capital recovery. It's called capital recovery because you're trying to figure out in equal annual amounts how much you have to take back to justify your original investment. So we go to n equals 8 and get the factor 0.17401. So that's 5 digits long. So in the end it means that we should round off our answer to 5 digits, or at the very least that's the only amount of accuracy we'll have. We won't be able to predict to the penny how much each repayment should be. So it should be $13.05 and 10 cents. Anyone else get that same amount? All right, good, good. Now on the back side of the paper is where we start to talk about gradients. All right, you'll notice that this cash flow diagram, I intentionally didn't add the years labels there. And the reason why I didn't is I'd like you to write the labels, and that's just to really drive home the point of when things happen in a gradient. One of the mistakes that I see students making semester after semester is that they will put the first amount that you actually see, so they'll put G in year 1. But G actually is supposed to be in year 2. And so here in part A it says write the years on the cash flow diagram, and that's hopefully, boy, annoying and persistent. All right, so just go through steps A through D here, and you'll notice it's for the 8% interest rate, and that factor table is on the previous page. So I'd like you to find P from this gradient, and also find the future value from this gradient.
I have a quick question about number 2. It's about the B.
Just give me a second, I'll be right back there. Okay, in the equation, the equations that are provided, what it means is the ratio of F to G is what's in the right side of that box. So the ratio of F to G is 1 plus I to the n power minus 1, and all of that is divided by I squared. And then separately we have minus n divided by I. Okay, I'm going to put the solution for problem 2 up on the screen. So it turns out that if we take this gradient to the present, then the value of that series is $930.02. Okay? And then if we solve for the future value is saying let's take it all to year 4. So essentially we're keeping the 600 in year 4. The 600 isn't experiencing any change in value due to a shift in time. It's just the 400 and the 200. So think about, you already know another way to do that. I mean, the quiz, you were asked to do something similar, right? You had to move amounts into the future, kind of one amount at a time. So if you wanted to do this manually, what you could do is say, all right, 600 is already at year 4. 400 is moving 1 year at 8%. So you compound it, 400 times 1.08. And then the 200 is 200 times 1.08 to the power of 2. So that would move it the 2 years it needs to go to get to year 4. Or you could just solve for the ratio. And so if we do that, put it into the equation, you'll notice that I've calculated these intermediate quantities here, the 56.32 and the 50. That's just so that when I'm double checking my answers later, I can check on the calculations part of the way through. You never want to just solve it the first time and assume you didn't punch the wrong button on your calculator. But in the end, what we should find is that the future value of that series is $12.65 and 28 cents. Okay, anybody else get that same value for part D? Any questions about this problem number 2, your first taste of how to solve a gradient? All right, problem 3 is another gradient, this time a little bit more tricky because you've got an annual series and a gradient on top of each other. Let's look at that cash flow diagram and talk about it before you start solving here. All right, what we could do is we could separate this into 2 problems. And when you're solving it, you have to think of it, you have to see the cash flow diagram a little bit differently. You need to see the cash flow diagram as, all right, we're going through year 5. So 1, 2, 3, 4, 5, and time marches on. All right, we are trying to find this unknown present value. And, okay, so 400 is there every time. And so the first thing we have is an annual series with 400 being the A. So A equals 400. And we want to find out what's the present equivalent of that for I equals 12%. So the way that we solve the first part of that combined cash flow diagram is this is find P given A, I equals 12%, N equals 5. All right? Simultaneously, on the same cash flow diagram, we've got a gradient. Okay, so what does that gradient look like? All right, what is the amount of G? G is 30, and when do you see G the first time? It's in year 2. So the way you can think of it is in year 1 is 0 G. Okay. Year 1 is 0 G. Year 2 is G, so there's 30. Year 3 is 60. Year 4, 90. Year 5, 120. All right? Yep. All right. We want to find out what's the present equivalent of that. So what is find P given a gradient, I equals 12%, N equals 5. So in one cash flow diagram is kind of 2 different problems. So what I'm suggesting is find the present worth of both of those components, and then all you have to do is just sum it together, and then that gives you the total present worth of this entire cash flow. All right, so dive into that. You can solve the, let's see, do we have the factor table? No, I guess I'm asking you to do it with the equation method. So use the equation formulas that are provided for the 12%. Now I'd like you to do this one by the equation method, just to get your hands dirty with some of these equations. So we need the P/A equation and the P/G. Let me paste those onto the page just so we can see it all at the same time. PA and PG, there it is. There's the PG. We also want the PA. All right, so we've got this cash flow diagram that we've broken into 2 parts. We've got an annual series where A is 400, N is 5, the interest rate is 12%. We've got a gradient where G is 30, N is 5, I is 12. We want to find the present of those two things and then combine it. So the first part, if we want to do the annual series first, then according to the equation method, we look up the equation for a find P given A, substitute in all the variables, we get this factor, 3.60477 ... That just means I left all the precision in the calculator so that I can report the answer to the nearest penny. So you multiply that factor by the given annual amount of 400, and the component of the present value that's attributable to the annual series is $1,441.91. And now we do a similar thing with the gradient, just except that the formula is a little more complicated this time. N is still 5, which is tricky, right? Because it looks like, why would there be N equals 5 when the amount is only years 2, 3, 4, and 5? So you only see the gradient, that extra $30 and increasing by $30 each year. You only see it in years 2 through 5, but still, the standard notation for a gradient is that 0G is still part of the series. 0G, 1G, 2G, and so on. And so back to the solution then, N equals 5 for that, and you get that the present equivalent of that gradient series of $30 is going to be $191.91. So the combined value then will be $1633.82. So I'll leave this up on the screen for a moment before we get back into the lecture notes here to talk about finding the interest rate and N.
I've got the intermediate substitution. Break it down step by step and show where you did it, or is it just all in the calculator? If it's just all in the calculator, it's kind of impossible to see where anything goes wrong. Like write out the steps like I did there. You're talking about P/G, right?
That's I add additional zero.
Okay.
Yeah, that's well. I thought that was zero.
All right, let's move on from this example. And of course, anytime maybe you fall behind on an in-class exercise, you can always refer to the video for the solution. Having these YouTube videos available means that you can go back and see the example as many times you want after class. All right, so part of economic analysis is finding out equilibrium between a present value and a future value. And so the idea of balance. And there's an analysis we're going to be doing where we want to make the equality between the present value of the inflows and the outflows. So money that you're receiving and money that you're paying out, we're going to try and bring into balance in order to solve for an interest rate. So for instance, look at this cash flow diagram. What this cash flow diagram is saying is it's saying that a present payment of $23,000 is the same as an annual series over 6 years where the amount is $5,000 per year. That may be true, but it's only true for one specific interest rate. It's probably not true for 1%. It's probably not true for 99%, but there is some interest rate out there where this is true. that those two things are in equilibrium. And so sometimes we need to solve for an unknown interest rate that brings equilibrium between the present value of the inflows and the present value of the outflows. And if we find it, it will bring the cash flow diagram into balance for some unknown interest rate. So here is the method that I'm going to demonstrate in just a moment. You'll have a cash flow diagram that's given, or maybe a word statement like text that you could prepare a cash flow diagram from the words that are provided. So you discount all of the future values to the present, and then you're going to combine it with any amount that's already at the present. So oftentimes that's an outflow because you'll be buying something in the present in order to get additional revenues in the future. And then we will iterate, so change the interest rate over and over until there's equilibrium between the present value of the inflows and the present value of the outflows. All right, now we're going to use Microsoft Excel for some of these calculations. There is an interesting quirk that Microsoft Excel has, and when we use some of the built-in functions that Excel has for financial calculations, it automatically changes the sign, so that if you put like a revenue into its formulas, it's going to tell you the equivalent cost. And so you notice how the arrow is up for one of these and down for the other. Microsoft Excel is going to always change the sign, and so sometimes what we're going to have to do is we're going to have to change it manually by putting a negative sign into the formulas, because maybe we actually want to have the signs stay the same. Like if we have some future value and we want to know the present equivalent of that without changing it from a revenue to a cost, then we'll have to manually correct by putting a negative sign into the function. So I'll show you that today with the in-class exercise that we're going to work through. We'll have to put a negative sign into the built-in formula. All right, so the in-class exercise problem number 4 that I've given you. Okay, so step A, draw the cash flow diagram, and then take the annual series to the present at 10% and at 12% and combine it with the original expenditure of $60,000. And I hope what you'll find is that if you're discounting it at 10% versus at 12%, in one scenario this investment is profitable, and in another scenario the contractor would be losing money. All right, let's look at the solution here. Your cash flow diagram should look like an annual series. Boy, oh boy, I'm really trying to keep my cool today. Microsoft doesn't make it easy. All right, so you're paying $60,000 now in order to get $16,000 each year for 5 years. So that's a cash flow diagram. Now, B is posing the scenario, what if you have to borrow money to do this at 10%? So whatever's happening here, the contractor borrowing money to buy this equipment, what if the contractor had to borrow money from a lender that's asking for a 10% rate of return? So the contractor is paying interest on the loan, and the revenue that the contractor is receiving, that's going partly towards repaying the principal, partly towards the interest, and then the contractor gets to keep some of the rest. What problem B tells us is how much does the contractor get to keep in the present? How much does the contractor get to keep in the present value equivalent of it, after repaying the loan? And so you know, the present value of these future repayments if you're discounting it to the present. So discounting is kind of the opposite of compounding. We've already talked about how compounding, when you're compounding amounts into the future, they're getting bigger and bigger. Discounting is when you're moving money backwards through time. Instead of moving it forwards through time, you're moving it backwards, and so the value of the amounts is decreasing because of the effect of the interest rate. So the annual series is worth $60,652.80, and when you combine that with the $60,000 at the present, then that means the present value is only going to be $652.80. So the contractor will be making a profit, although it's pretty modest for a 5-year project. So that extra revenue is worth $652 in today's terms. But what if the contractor needs to borrow money at 12%? You know, maybe the contractor doesn't have the best credit record, and so the interest rate is higher, perceived more of a credit risk. Well, in that case, actually, it's going to be a negative value because those future amounts get discounted more heavily at 12%. And so what this all means is that the value of the project in terms of the interest rate that brings everything into equilibrium. Remember the picture of all of the balance and the equilibrium. If we're solving for some unknown interest rate, the rate of return for the project, it's going to be an interest rate that's between 10 and 12% because it's that crossover point where there's balance between the inflows and the outflows. In part B, the inflows are too big. In part C, the outflows are too big. So what we want to find is what is the interest rate for this project. And so I'm going to demonstrate that with Excel. And if you'd like to fire up Excel, you can. It's probably better just maybe to follow along this first time just to observe it. And if you'd like, you can go back through the recording and do the similar calculations. Just to test, to make sure I get my spreadsheet set up right, I'm going to start with 10% interest. I'm going to have a column that's the year. Let me make that a little bit bigger so it's easier to see. I'm going to have a year column, a column where I put in an amount, and then where I'm going to have the present value of an amount. Okay, those will be my columns, and I'm just going to represent the cash flow diagram as a cash flow table. So I want to have the same 5 years and the same amounts, negative 60,000, and then I had 16,000 each year. All right, now the present value of the amount. I'm going to try and calculate what is the present equivalent of that amount, and I'm going to do it with the formula equals PV, and it asks me first of all to put in a rate. So I'm just going to click on the cell where I have the interest rate, and I'm going to anchor that reference by pressing the F4 button so it always looks in that same cell even when I drag the series downward. Okay, NPER means how many years are you shifting the amount forward or backwards in time? And in this case, it's 0 years. All right, put in a comma, and it's asking what is the recurring payment amount? And these aren't recurring payment amounts. We're going to be treating them just like a single amount. So I'm going to skip over that field, and then here as a future value, I'll put the negative of the amount. And remember I mentioned that some of Excel's built-in functions will change the sign on you unless you manually override by putting in a negative sign of your own. This is one of those cases. All right. Now, it turned red just because one of the formatting styles that Excel has, like some account ledger method, does it that way with the parentheses. I prefer that we just switch it to currency because that makes more sense to me for it not to be red and with the brackets. So what it's saying is $60,000 moved 0 years into the past is still worth $60,000. But if I drag this formula down through the entire series, what we're going to see is that each one of these amounts is worth progressively less and less. So that's saying that 16,000 5 years from now, if you move it to year 0, that 16,000 is only worth, in today's dollars, 9,934. So that makes sense because it's discounting fewer number of years than the amount that's received in year 4. I'm going to create a sum field where I just kind of add everything up above it. And what we're going to look for is to see, is that the same as what we got here? $6.52 and 80 cents. So it is consistent. What we've done is we've just discounted each year to the past. So I use the PV function here. I didn't have to use the PV function. I could have done 1 plus I to the negative n power. That would have given me the same thing. Let's just test that. It'll be this times 1 plus I to the power of minus n. Okay, if I drag that down. Oh, I didn't anchor a cell reference. All right. So the PV function is doing the same thing as P equals F times 1 plus I to the minus n power. And that's straight out of the equation table that I've given you. All right, so this was for 10%, if I express it as a percentage. So there's 10%. What was it for 12%? So let's check and see if I put in 12%, it should change all of the amounts. Everything's going to be discounted more. So see this 9,934? If you're discounting at 12% per year instead of 10% per year, it's going to be worth even less. So now we've got that negative 23. So what we want to do is we want to find out what is the interest rate that causes this to be 0. So is it 11%? Getting closer. Is it 10.5%? Getting closer. 0.0104? Oh. 10%? All right, so there's a tool in Excel, data, what if analysis, goal seek. What I want is I want this to be 0 by changing the interest rate. And I'll tell it to go. And it's going to play around and it's going to find the perfect value for the interest rate that causes the sum to be 0. So what that means is that the rate of return of this cash flow diagram, this business opportunity, has a rate of return of 10.425%. So that is the rate of return of this business opportunity. All right. We can also use a function called the rate function. And on the handout you've got, it says observe the Excel solution using the function rate. So watch how easy this is. You just do equals rate and NPER. So the number of years is 5. The payment amount is 16,000. And then the present value is negative 60,000. Now hopefully we don't need to make adjustments for sign, but and then I'll have it display more digits, and it's that same 10.425%. So the nice thing about Excel's built-in functions is that when you start one, RATE, parentheses, it starts to give you hints of what it needs to see. So NPER means the number of years. PMT means what is the annual series payment amount, 16,000. The present value, negative 60,000. And we could have just clicked on those cell locations in addition to typing it in. But we get that same 10.425%. So there's lots of different ways to find out what is the unknown rate. All right, we only have 3 minutes remaining, and I promised to give you some time back, right? I owe you 1 minute plus interest. So here's what I'm going to do. This problem 5 with the unknown n, I'm going to send you the solution to that as a PDF file, and I'll also I'll keep working, but I don't expect you to stay, just so that there's a demonstration of this solution on the video. So I'll send you, along with the PDF file, I'll send you a link to today's lecture that starts at this point in the video so that you can see the illustration how to solve problem number 5. All right. That's it for today. I'll see you on Tuesday. So here's the solution by hand. If you've got A is 8,000 and P is 60,000, this is the ratio factor, and you can find that closest factor between the 14th and 15th year. So 14 years doesn't quite get you there, but then 15 years is breaking even. Now, by Excel, in this problem, 10%. Of the year column, an amount column, PV of amount, and cumulative PV of amount.
And then I want to work on her physics. I think, yeah, he's going to do the homework.
60,000 payment, and then you're getting 8,000 each year. We want to know, when do you break even? So we got to find the present value of each. So equals PV. The rate is this. Anchor the cell reference. N is the row that you're on. Skip over the payment field, and it's going to be the minus of the amount for the future value. And the cumulative PV, it's the amount for the first year, and then the one above it on the side. One above and the one at the side.